Welcome back. This is going to be a kind of continuation of my last few videos. We have broken down the actual ventry of the intake system and addressed some of the reversion that is occurring. So today we're going to be talking about port tuning and the things within a engine that actually contributes to port tuning. Now, in the comment section within the last couple of videos, individuals have asked about obviously the different valve sizes, what it contributes to additional horsepower, what creates more torque, or what determines where the torque is occurring within RPM. So we're going to go through a list right here and possibly a drawing to identify some of the things within an engine where port tuning actually occurs. Now, for you more modern day individuals, the word tuning refers to a lot of the things that are happening within the electronic control module and the different timing within the camshafts with the dual overhead cam type system. So the VTEC, let's call it that. So your little sport compact tuners, their entire emphasis behind performance is the ability to adjust the tune of the engine on the fly. So again, within the different RPM, they can alter the timing of each individual camshaft, the ignition timing, the fuel delivery. All of it's tied together to where the AI, the artificial intelligence of the onboard ECM, will help mitigate the actual tune. We didn't have that with older engines. Okay, so realizing the carbureted engines of the muscle car eras, we didn't have the computer technology to be able to help us in diagnosing the tune of the engines. So each engineering individual for all the manufacturers, they had to understand where the tuning came from within the actual design of the engine. Its sole intended purpose. So while some of the engines were designed to, propel a very heavy vehicle, whether it be a truck or a station wagon or something with a full frame, once you start getting into performance and changing the actual components of the engine, it changed everything outside of the original design. So again, going back to that 1 to 5,000 RPM power band was the initial intent of most of your muscle car engines. Now, obviously, through a few different modifications, those numbers could be achieved or shifted to the point where maybe it was 2,000 to 6,000 RPM, just by changing some of the tuning aspects or mechanical mechanisms within the engine. So I had the list here. We're just going to go over it. Obviously, the ventry of the intake system. That includes the ventry of the carburetor, the size of the intake ports, when the velocity and volume is contributed to the RPM range, and how big the bowl area is compared to the rest of the port, referring to the reversion. When is the reversion backing up into the port, creating a restriction on the new incoming charge? The more efficient you can get rid of that or limit the amount of reversion, the more the fresh air and the more efficient the port is going to be. So there's a lot of different things into it. Obviously, the bowl is what I got written down in there. The bigger the bowl, the more air that can be crammed in there during the ram effect. Now, many individuals forget this. When an engine is on its intake stroke, as the piston is approaching top dead center, the valve obviously closes as the piston is very close to top dead center. And as it travels away from the valve, it's not necessarily creating any kind of vacuum. So there isn't a natural vacuum source to initiate the airflow past the valve. It is actually the ram that is built up in the bowl area that initiates airflow into the cylinder. Okay, even with the most advanced exhaust systems out there that can evacuate the previous ignition sources and flame front, they don't get rid of everything. So there is a negative pressure within the cylinder when the valve is initially opening up. But it's the ram effect that actually gets the movement going. So reducing the reversion as short as you possibly can with an intake system allows the entire system to ram the force and the pressure within the bowl area. So the larger the bowl area, the more volume of the next intake charge is available at lower lift numbers. Now, tuning is not just inside of the intake system itself. It actually occurs from the piston travel also, because again, as the piston is leaving top dead center, the speed of the piston and the volume, the area of the actual bore of the cylinder, dictates when the intake port is receiving the most amount of vacuum. Again, the piston normally is extracting the most amount of vacuum at approximately 50% of the travel within the cylinder. But from top dead center to 50%, the efficiency rating, the increase of speed from top dead center to that point, is dictated by multiple different things. It could be from the crank, the stroke of the crank. The larger the stroke, the faster the piston should be traveling, but that is altered by the connecting rod also. So again, going back to the small block Chevy, most of your engine combinations, whether it be from Ford or Chrysler, they stuck to a certain connecting rod length, and they may have altered the stroke of the engine to mitigate or to shift around the cubic inch. Small block Chevy, you go back, and even the 350 used multiple different connecting rod lengths. So whether it's the 6-inch, 5.7, or even the 5.5, obviously not exact numbers, that altered piston speeds directed towards the specific RPM that the engine was designed to operate at. So again, with the longer connecting rod, it caused the piston to hang out at top dead center for a longer period of time. In order to speed up the piston, you actually had to go to a shorter stroke. So it was a balancing act between that. And Chevy's engineers, even Smokey Yunick, played around with different connecting rod lengths to alter the rod to stroke ratio. Now that rod to stroke ratio plays into the port tuning, because that is when it is going to be exposing the vacuum and how aggressive that vacuum is transferred onto the intake port. Okay. Now the valve also affects port tuning. Depending on the face of the valve, let me grab one here. Even the valve face right here, the cup portion, will dictate the tune of the reversion. So with all valves, when the valve is closed, either on the exhaust stroke or the intake stroke, there is pressure that builds up underneath the valve. And if you have a cupped valve, such as this, let me see if I can get the right reflection, the depth and the size of this cup will also tune the amount of reversion that goes back around the valve. Okay, so factory engines, this just happens to be a factory Chevy valve. While the numbers are very minute within RPM range, the actual valve can control when the tune of the port is precisely matched. So all of the components of the engine, I don't know how to beat this into your heads any further. The engineers of the muscle car era, they may have altered some of their designs from the different manufacturers, but they were all trying to meet and create components with the engine that all work together. So even the valve, not only the valve diameter, but the valve design itself, whether it be the nail head or the tulip design and the cupping of the valve, was part of the port tuning of where within the RPM range the engines were designed to be operated in a continuous motion. Not necessarily through the acceleration, but where the engines were held at RPM. So normally cruising speeds of where the engine is supposed to be most efficient. Remember, even before the gas shortages of the early 1970s, the engineers still designed engines around a certain RPM range and for a certain purpose. It isn't until the aftermarket or performance industry took those original designs and started modifying them that it changed the port tuning. Okay, all the things that we just talked about, piston speed and the rod ratios, that's also going to alter the port tuning within the RPM range. So the port has to match the piston speeds, the vacuum that's created, to allow it to get the most efficiency or the most power per cubic inch within the RPM range, wherever that may have been intended. Cubic inch, again, the larger the bore or the larger the stroke, will increase the amount of demand that the engine has to fill the cylinder. So a large bore, even with a short stroke, the piston speed is increased. And because of the area around the valve and the larger bore, it deshrouds the valve. So a little bit more is put onto the actual combustion chamber design to allow more of that air to transfer when the piston is near top dead center. Okay, as the valve is opening, once again, there's no vacuum necessarily pulling the air past the valve. It is the ram effect, the pressure, the positive pressure on the backside of the valve, and the lower pressures, not necessarily negative pressures, but the pressure differences between the cylinder and that. And the bigger the bore, the more area is there to be filled. So the pressures will be a little bit lower on the cylinder side of the valve. Again, as the valve opens up, it is the ramming effect. The most you can get into there, in behind the valve within the bowl, is going to initiate the airflow sooner. And the bigger the cubic inch, the more vacuum it's going to create, without increasing the speeds of the piston through the stroke and so on and so forth. The shorter the rod and the shorter the stroke, the faster that piston is going to be traveling from top dead center to approximately halfway through its travel. So it's going to be in a very aggressive vacuum creation. As the piston travels down, the creation of vacuum is going to increase. Initially, when the valve opens, it's not creating any vacuum. Until you get into the exhaust system. We're not going to get into that quite a bit yet, because the exhaust system has a lot to play, again, within port tuning. Not only to the exhaust port, but what kind of pressures are left behind in the cylinder. Normally at lower RPMs, the exhaust gases can get out fairly quickly. But as RPMs increases, some of the air does not make it out the exhaust. Okay, so again, the ratio between intake port flow and exhaust port flow also contributes to port tuning. Valve orientation. A wedge style type combustion chamber inline valve. As the valve opens, in previous videos, as I claimed, there's material of the engine block or cylinder head that creates a resistance to flow, blocking out vacuum that can draw in the next fresh charge or to address the ramming effect. With a canted valve cylinder head, the valves are moving away from the restriction. Now, many people do not realize this is the angles. So a straight line non-canted engine, whether it be 23, 20, 18, or even 6 degrees, as somebody brought up, the goal is to open the valve to allow air between the highest concentration of vacuum and the port. So typically the best orientation of valve angle is contributed to the actual height of the intake port itself. So as the valve is canted from, say, 23 degrees to 18 to maybe even 15, there's a relation between the height of the port and the approach to the back of the valve. Majority of engines are designed to where the maximum velocity of air, once the vacuum is being exposed to the port, the air will actually travel across the valve. It is not traveling all the way around the valve. It is favored to one side. So that's why there's a curvature to most of your intake ports. They're not a straight shot. Okay, so taking in accordance of why the port is actually curved addresses the air-fuel mixture rating. So most of your short-term radiuses are preceded by a ramp. That ramp is to introduce fallout of the fuel. Again, during the reversion, when the reversion is backing up, the fuel can actually be allowed to accumulate into droplets, which is bad for performance. Now, those heavier droplets will drop to the bottom of the port. The higher velocities normally travel at the top of the port. So by having a ramp on the short-term radius, what's allowing it to do is the vacuum that is being pulled over the short-term radius from the valve and the port or the cylinder itself, it is pulling the heavier fuel molecules up into the higher portions or the faster portions of the velocity of the port and the air movement. They meet basically at the back of the bolt area and on the valve at lower RPMs. As RPMs increase, it's much more important to open that area between the seat and the valve. The curtain area, again, is going to be very important. It allows more of the vacuum to be exposed to the port. So all of those parameters need to be overlapping. All of the parts have to work together to allow each component to function within its intended performance range. So again, engines from the factory are designed in that 1 to maybe 5,000 RPM. Once you manipulate or change even one aspect, even one component of the engine, it takes a totally different ratio to figure out exactly the proper port tuning. And this entire list contributes to when a port reaches its most efficient point. Cam timing also alters that. Again, going back to the newer sport compact tuner type engines, the cam timing is done by the actual readings on the computer, monitoring the exhaust and the amount of fuel that's being injected in, and also altering the timing of the cams, whether it be one at a time or both simultaneously, to create the best port tuning for the RPM that the engine is running at. The computer, the technology can control that to the point where the most efficient port tuning is achieved no matter where in the RPM range the engine is spinning. The older engines, it had to be the individual builder designing the engine around its intended RPM range. So if you're in circle track racing, it was all about that 6,000 to red line portion of the RPM range where all the components were designed to work together. And if you had restrictions within the components, obviously using either factory heads or parts that were authorized by the association, you knew what components you were restricted to or modifications that you were not allowed to do. So the only thing that he gave you to alter was basically within the cam timing, even with lift or duration restrictions. Cam timing altered the port tuning in that 6,000 to red line RPM range. So again, even little things like the cupping on the back of the valves is contributing to when the reversion is occurring around the valve at each valve event and how much air is being diverted towards the exhaust. Again, with inline valves, the only orientation to the valve is directly to the cant within 0 of the block, to the center of the block. Okay, so it's going to be 23 degrees from the deck surface in orientation to the center of the block. the perfect 90 degree. Canted valve engines, if you'll notice the big block Chevys or Ford Clevelands, the valves are not canted to the point where they open towards a wall. They move away from the wall while restricting it, allowing a bigger portion of the area of the curtain area to allow the air to flow through. But when the valve is closed, it's actually still operating. It's blocking off the intake charge, but as the piston is moving up on the exhaust, that pressure area underneath the valve is also directing the pressure towards the exhaust side of the combustion chamber, or directly into the exhaust curtain area. So again, the engineers behind the porcupine cylinder head of the big block Chevy were not just taking in consideration of the intake flow and opening it up to be less restrictive. It was also addressing once those exhaust gases or once those combustion gases were ignited and the pressure was used up, was to direct that used energy source towards the exhaust valve side of the combustion chamber. And they will have different styles of valves. Normally, the big block Chevy with a cant or any canted valve cylinder head, they will have a flat faced valve, because once mated up to the seat, it creates a wall for the air to basically be pushed up from the piston directed towards the exhaust. Okay, now that is normally something that's going to assist your port tuning at lower RPMs, but we know that at higher engine RPMs, even with a non-canted engine, again saying that 6,000 plus, having a flat-faced valve allows more of the pressure to be shifted to the other side of the combustion chamber. Normally, all of your exhaust valves will still have this cupping orientation or design within the valve, because the air is only moving in one direction, basically in the intake, over the intake valve. And by having those pressures built up in the cup, it creates a pressure zone that is spherical. So again, the pressure becomes kind of like a mechanical device. Even though it's a compressed gas, it creates a gaseous border. Let's call it a force field. Okay, for some of your truckies or techies out there, it creates a force field to where the exhaust gases are directed more towards the exterior of the exhaust valve without using a mechanical device. It's using the pressure built up in that cup area to create that sphere. The intake valve, in that same orientation, while that is occurring, it's closed. As the piston is traveling up on the exhaust stroke, the valve surface area, if it is flat, it's actually pushing more of the exhaust gases towards the curtain area of the exhaust. The gases that are going straight towards the face of the valve, they're being diverted by that force field, that higher pressure area created by the cup of the valve, of the exhaust valve, to push more of the air towards the exterior or perimeter of the exhaust valve. So by increasing the exhaust valve size, is there necessarily any performance gained within doing that? Again, it's related to the port tuning. Majority of your exhaust gases exit the moment the exhaust valve leaves the seat. More than 70% of the exhaust event actually occurs within the first 250 thousandths of the valve lift. The lazier amount of pressure that is left behind during that time is then forced out by the movement of the piston, actually creating a higher pressure zone between the piston and the combustion chamber. But most of your exhaust event or movement of air actually occurs in the very short lift numbers. So again, this pressure area is going to alter at certain lift numbers and also during different events within the pressure zone of the compressed gases within the cylinder. Port tuning is dictated by the cam timing, the actual design of the valve, and the exhaust port. The faster you can get exhaust gases out and allowing that pressure in the cylinder to actually creep up a little bit will help force the exhaust gases in one direction. Now, just like the intake port has reversion when the exhaust valve or when the valve closes, there's also reversion in the exhaust system. So port tuning is when you're addressing the amount of reverse flow of the exhaust gases coming back into the exhaust port of the cylinder head itself. Mitigating when those two forces meet is dictated by the RPM range and the restrictions in the exhaust. So anything you can do to reflect any of the reversion coming back will allow your exhaust system to be more efficient, getting rid of the initial exhaust gases at low lift numbers, and then also helping the lazy air pressures as the piston is coming up, that other 15 to 20% of the exhaust air movement, you need to keep the reversion as far back in the exhaust to allow those lazier pressures to get out. Okay, so that's done within cam timing and also within, piston speeds and port tuning as a total, including all of these different mechanisms. Somebody had mentioned in previous comments, what about the Oldsmobiles? Now, each manufacturer, once again, they design their combustion chambers around achieving a certain compression ratio and also to address the flow or the tune of each intake and exhaust port. The Oldsmobile was a little bit more specific to when and how they approach the port tuning of the intake. I'm just going to talk about the intake at this point. Now, I'm going to draw just the short-turn radius or the port floor between a small block Chevy, small block Chrysler, compared to even some of the small block Fords or the Oldsmobile or Pontiac designs. Now, the short-turn radius of the small block Chevy includes that ramp. Once again, that ramp is there to initiate or to introduce more of that fuel molecules that have dropped out back into the high stream velocity area of the top of the port. The ramp is fairly close to the actual bowl area of the cylinder head. Oldsmobile is probably the most extreme variant of this port tuning and the ramp going into the cylinder head itself. You'll notice that it doesn't have that abrupt ramp right behind the short-turn radius like the small block Chevy. It's a continuous radius that goes all the way around. So it's not initiating or it's not kicking up the fuel molecules into the highest velocity stream of the intake port until it actually reaches the back of the bowl. Okay, so in order for the Oldsmobiles to get the efficiency of fuel mileage compared to the small block Chevy, it has to occur at a higher RPM. So if you compare a 350 Chevy compared to a 350 Oldsmobile at 2,500 RPM, the small block Chevy will get better fuel economy. It does. Okay. Now, the level of the intake port, again, associated to the valve angle itself, again, even though the valve angle of a small block Chevy is 23 degrees, the valve angle of the Oldsmobile is canted over quite a bit more. But in relation to the port angle itself, the approach, the small block Chevy is higher. The Oldsmobile is much lower. Okay, so even in modern day engines, let's go back even to the late 1970s with pro stock engines or modified aftermarket cylinder heads. For Chevy, the 18 degree raised port cylinder heads, the big block, Big Dukes or Big Chief cylinder heads, they all have that raised port orientation. Even the newer LS engines have that higher port with a altered valve angle. Typically, the relationship between the port angle and the valve angle are married. So again, the small block Chevy has a 23 degree valve angle, but the port orientation to that angle is the exact same as the 18 degree small block Chevy. So even though the valve is canted over to the 18 degree from 23 degrees, the port is also up a little bit more. They're conjoined. Okay, so with the LS engines, with the exception of the LS3, the port entrance and angle to the valve angle is to address the air and the valve moving outside of the actual highest velocity region of the port. It is not a direct relation the air is not being derived to go all the way around the perimeter of the valve equally. It's being favored to that side of the bowl area. So the valve opening needs to move away from the area. If they keep it within line, say the valve is now open, if the air is moving straight to the angle of the valve itself becomes a restriction to the airflow path. By canting the valve, the valve is opening up, exposing more of the higher velocity areas of the incoming charge. The valve is moving out of its way. And the more that valve is canted, the higher the floor or the approach of the port needs to be to continue keeping the airflow moving in the largest area created by opening the valve. And that's also in conjunction to the angle of the banks of the engine. Okay, so for you Harley guys out there, you know, it's the difference between the V of the Harley Davidson compared to the angle of the typical V8 engine. Okay, that alters port tuning. But between the Chrysler, Ford, and Chevy, the original engineers behind those combinations were looking for engines that operated in that 1,000 to 5,000 RPM range. So by altering any one of these mechanisms or components, you have to redesign all of the rest of them to also work together. in your specific RPM band. So if you're going to modify your cubic inch with a stroker engine, you also have to realize you need to modify the cylinder heads and the intakes, or even the carburation and the cam timing, to take advantage of that additional vacuum that will be created by the larger cubic inch. If you change connecting rod length, it's also going to alter the piston speeds of when it is actually creating, or how aggressive it's creating the vacuum within the 50% travel of the piston itself within the cylinder. The valves, once again, it occurs in both directions, not only when the valve is open, but what is the air doing when the valve is closed? Is it initiating airflow from one side of the cylinder to the other? Is the orientation of a straight valve engine allowing the air to swirl in the combustion chamber? And at what point within that swirl is the exhaust valve opening? Do you want the flame front to be right directly underneath the exhaust valve when it starts to open up? Yes. Okay. You want to get rid of those expanding gases. As soon as they've been spent to create the energy to force the piston down, you want the highest velocity of those gases to occur directly underneath the exhaust valve. And extremely high RPM engines, or extremely high efficiency race engines, you can determine how efficient your combustion chamber is by the carbon print that is left behind. If you're utilizing aluminum cylinder heads, you can look at your spark plugs and diagnose your air-fuel ratio, so on and so forth. But when you actually pop the cylinder heads off, the carbon print on your combustion chamber, if it's completely black, you're not achieving the proper port tuning. If you have a narrow carbon print between the intake and exhaust valve that's very narrow, and it doesn't include the entire perimeter of the combustion chamber, you know you have achieved premium port tuning. It means that it's actually allowing the gases to be burnt precisely where it needs to be. None of those burnt carbon molecules of the exhaust gases are sticking to the combustion chamber. They're being burnt efficiently that by the time they reach underneath the exhaust valve, they're going right out the exhaust pipe. So little telltale signs of even the condition of your valves or the carbon printing on the combustion chamber will tell you if all of these mechanisms are actually working together the most efficient. You will also see on dyno or performance test, engines in that orientation will achieve the maximum power that they're capable of making. You can't get any more out of them without going to forced induction. Okay, so hopefully it's helped out a few individuals with the questions that came out. If you are a novice or somebody that's just getting into this, or if you don't understand the level of technology here or science behind this, if you have a capable machinist or an engine builder, one of the very first questions they should ask you is, okay, you have this engine or you have this combination that you would like to put in such and such vehicle. What the very first question that should come out of them is, what is your intended purpose? Is it going to be a daily street driver? Is it going to be something that's a street strip? What is the combination of street strip? Are you going to be driving the car to the drag strip every weekend, then racing it and then driving it home, so it's a 50-50 street strip combination? Is it something where you want to be able to drive a race car on the street, so it's got to be able to live stoplight to stoplight for very short distances, but it's primarily used for racing? Is it a show car to where you want it to really sound nasty and stuff as you're approaching the show, but then it's going to be sitting there and just for looks? Is it something that, are you going to be driving it at 65, 75, or 70 miles an hour consistently, these are the type of questions that will alter the engineering aspects going into the build to address when the port tuning needs to be the most efficient. It's not about maximum horsepower or maximum torque. In the past, when I was in the machine shop service and engine building services, I asked those type of questions to my customers. Most of the time, they had a very clear idea of what they were trying to accomplish. If they wanted something that was completely gone through using factory equipment, let's just use a small block Chevy for an example here. Say somebody had a Camaro and they want something that's a little bit more high performance, something they will still be able to drive as a daily driver, but also be able to take it to the track occasionally throughout the year. Knowing that we have to work with factory components or even some of the direct copies within the aftermarket of maybe an aluminum cylinder head, so on and so forth. Every single one of these aspects needs to be engineered into the design for its intended use. The customers would always be happy with the final results. It wasn't necessarily about maximum horsepower, because just by altering the cam itself, I could take an engine that was a healthy 350, let's say, that could be driven on the street, get fairly good fuel economy, be able to cruise at 65, 70 miles an hour, and achieve 400 horsepower, and have a happy customer. If the customer was all worried about dyno numbers, without changing anything at all within the 350 except for the cam, going to a larger cam, I could create a 350 that made 500 horsepower, which looked really good on the schematics from the dyno. But as soon as the engine was dropped into a car or a vehicle of the customer, it was a complete dog. They're happy with the numbers and the paperwork from the dyno, but it was junk on the street. So stop. This is just a little piece of advice. Stop looking at maximum numbers. Look at your intended purpose and maximize the components to operate in that purpose. With cylinder head flow artists out there trying to market their products to engine dyno gurus, they're also marketing components to achieve that 500 horsepower. Many customers that have gone through engine shops they're trying to get the most amount of money, promoting more expensive components that they make more profits off of, does not make a happy customer. Okay, they might see the higher dyno numbers and give them maybe some bragging rights when they get to a car show of like, yeah, that makes 500 something horse. Okay. But driving at home, you're constantly feathering the accelerator pump. The engine overheats. You get 5 miles to the gallon instead of 20 miles to the gallon. Okay. If an engine builder knows precisely what the intent of the engine is, every one of these aspects is going to be included into the build. And it does not necessarily require aftermarket components. The engineers from the manufacturers designed it originally around the fuel and the intended purposes of muscle car engines. That simple. With that, yeah, a lot of videos here recently. I have other things going on, so it's not something I'm going to be continually doing every single day. We are just covering topics that individuals are being misled with. It is the way the industry has gone. The performance industry is all about marketing, creating more money flow through the aftermarket. But it's one of the reasons why some of these sport compact tuners have left the muscle car chassis in favor of these smaller engines. They can get the performance and they can also get the fuel economy to where they can drive it on a daily basis. Say they're a college student, they can drive their cars back and forth to school, get 25 miles to the gallon. And then when they want to, they can just put the accelerator pedal to the floor and outperform some of the muscle cars. True engine builders will build you an engine that will fit precisely in your intended purpose. Whether it's a mud truck, drag car, road course, show car, daily driver, it's all designing the original engineering from the manufacturers. But with the older engines, you need to be more precise of the components going into it because they don't have the AI helping them do the job for them. Have a good one.